All right, so this talk is on climbing the mountain of database reliability. But before we get started, here's a mandatory slide from the organizer. I've seen it 3 times already, but I'll still have to read it. Thank you for joining us at the 11th Annual Denver Solid Weeks. Thank you to our title sponsor, Amazon, Capital One Cafe, Dell for Startups, and Downtown Denver's partnerships. This session is part of the developer track sponsored by Quizlet, one of the 8 programming tracks aimed at supporting the entire entrepreneurial team. By attending this sessions, you are agreeing to follow our code of conduct as well as to be photographed and video recorded. Be sure to share your experience at these sessions online using Denver Startup Week and #Quizlet. And here's a list of sponsors. And here's another list of sponsors. All right, so let's get back to the talk. What is this session about? Right? What is climbing the mountain of database reliability about? So if you work at a company with large amount of user-generated content, you're constantly trying to scale your data source to accommodate for the demand. So this is our journey at Quizlet, trying to scale our database layer. And our approach evolved over time as we learn more, and then we're trying to define what database reliability means to Quizlet as we work with other teams. A little bit of background about myself. My name is Mason. I am a SRE turned data eng at Quizlet. I've been at Quizlet for almost 4 years, with an office in San Francisco, an office in Denver, one in London, and one in New York as well. So coming from an SRE background, I have very heavy backgrounds in infrastructure, systems, and reliability. And I often view myself as a plumber for our infrastructure, making sure that our bits are going through the pipes correctly and safely and quickly. And I think the same thing applies to the data source. So what is Quizlet? So Quizlet is in the education space. One of our mission statement is to help students as well as teachers to practice and master whatever they're learning. Now BTS, which is not the Korean boy band, stands for back to school seasons. That is a period that we see a lot of high traffic, and that BTS is actually happening right now. It is for us, it's between mid-August till October. As of now, yesterday when I was checking what is the RPS on our edge, we are serving an historical high. But hopefully our infrastructure is still humming. So I'm the first engineers who actually focus on database reliability, and we're still kind of figuring out what that is. And I think a lot of companies are doing so. Okay, so here's a little bit of background about what our data structure, our database layer looks like. It's really simple. It runs in GKE, which stands for Google Kubernetes Engines, with a bunch of web applications running, and they connect directly to our MySQL clusters. And the MySQL cluster is running in Google using Cloud SQL for MySQL. So that is a managed service offering by Google's. So after BTS 2020, we noticed a very worrying trend. Now for those with keen eyes, you can see that we have a bunch of spikes after those red boxes. So to give a little bit more context of what that is, on the right-hand side, the vertical axis is the database connection count. And then those red boxes are code deployment. Because we run a blue-green deployed, every time that we do a code deployment, we're going to double the number of connections. And then we have a 15 minutes kind of cool-off period. That means within that 15 minutes, we're going to double the number of connections. And the worst thing is, for our database, right, we have a maximum connections of 4,000. So if you look at the graph, there are times when we hit close, very close. Sometimes we hit 3,000, sometimes we hit 3,200. And in the worst case scenario, when we have a rollback, if we have to do a rollback within 15 minutes, that means we're gonna triple the number of database connections. So that is something very concerning to us.
Where does this 4,000 come from?
Great question. Comes from Google.
Yeah.
So even though in the past they have a hard limit for Cloud SQL connections, they hard coded to 4,000 and you can't get above it. They have lifted that limit to something, I think, above 10,000, but don't believe in it because it depends on how you handle the connections between your database and your web. So depending on how you set all those different database parameters, what we notice is when we get above 4,000, we start to see instability. So we put a hard floor on 4,000.
But Google manages those connections, right? They have the sidecar, the container that does the connection.
They manage the connections, but then your database connection also depends on your RAM as well. So okay, so for a Cloud SQL instance, you have CPU and then you have RAM, and then the RAM is fixed. So if your connections consume a lot of, say, resources, so even though ideally you can set something like 12,000, but you will never reach that, and that's what we're seeing because of how we configure our databases. Yeah, so it was very clear that we have to do something about our database connections. Otherwise, we're going to hit a scaling wall come BDS 2021, which was last year. So as an engineer, our manager always encouraged us to think big. So we start to really think big. We were thinking about what does the next generation of data store look like for Quizlet, right? We begin to write out a laundry list of restraint or complaints about our infrastructures. So first off, we have the maximum database connection limit. We have a single point of failure in the primary, right? Because for MySQL clusters, you have a primary and then you have a bunch of replicas hanging off it. So you have a spot in your primary. You can have replication lags. And with MySQL, when you bring up a new replica, you have to basically copy your entire data set into another place. So that increases your storage cost as well. And with our setup, we can do sharding. We can scale vertically, but we can't scale horizontally. At least not easily. And then we can't really geolocate either. So when you start looking at the list, there's a lot of things that we don't like. So we began to look at a distributed data store, right? Everyone maybe have looked at it before. It's new kids on the block. It is supposed to give us infinite runway for our databases and just remove our problems completely. And that's what we thought. So we spent 2 months doing a POC on the distributed data store, and it turned out that it was too difficult, and the lift was really big. The lift, it was really, even though they claim it to be, and they are MySQL compatible, there's a lot of things that we found out during the POC. For example, the middle layer, we have problems scaling the middle layer. So through load tests, we found out that we can't move to a distributed data store. And then one thing at the end of the POC we learned was often we overlook the simplicity of an infrastructure and something that has been ran for a long time and well understood. So we took a step back and think about what are we trying to solve here? What is the challenge that we're trying to fix? It is a database connection limit. So we began to think, is there a way that there's something that can optimize and we use our database connections so we can lengthen our runway for existing database layer. So after talking with a bunch of engineers from other companies, a product came out. It's called Proxy SQL. So Proxy SQL is an open source application that manages your connections between your applications and the database. And one of the core features is something they call multiplexing. So multiplexing is the ability to basically reuse and optimize the way your connection is set up. And the good thing is it is really small. It has a very small footprint, so we can easily fit this into our Kubernetes clusters. So we spent about a month trying to figure out, okay, is this gonna something that would work for us? And after a month, I think that yeah, it is simple enough that we can fit this into our infrastructure. So conceptually, what we are trying to do is really simple. What we're doing is taking your entire production database traffic, lift it up, pipe it through the proxy SQL, and then let it send to the database. So after the POC and after the implementations, as we roll out the proxy SQLs, I think there are a couple of pointers that's worth noting. And this also applies to any kind of migration that you plan to do. So first is always have a backup plan. Before we even get proxy SQL into productions, we implement a bunch of feature flags that allow us to control the traffics between the web applications to the database. So we have 10 different databases running in the backend, and each one has its own feature flags that can switch traffic between 0 to 100%. And then we also have a global kill switch that if we flip this on, we can bypass proxy SQL completely and just fall back to what we used to do. So always have a backup plan. Second thing is manage your expectation by communicating loudly. Make sure your manager is in the loop, because as you are fighting fire, your manager is the person who's going to handle the communication, especially from executive. And also the best migration is always uneventful and boring. Take small steps, right? Ensure that you can observe as you migrate. For our databases, because we have 10 different databases, it took us 10 days to migrate. Each day we migrate one, and then we let it sit for 24 hours, just to see if there are any spikes and anomaly. And then lastly, do lots and lots of load tests. One of the questions that came up a lot with proxy SQL was, we're fitting something in the middle. Is it going to increase our latencies? So in the POC, we run a lot of synthetic load to find out that the latency was small. And then when we are actually piping production traffic over, we look at both the P50 and P99 latencies. We didn't notice anything changes in the P50, and for the P99 latencies, we only saw a few milliseconds increase. So with data, you can present to your fellow engineers and say, this is not going to be an issue when we put this into production. And this is what the graph looks like after we finish the migration. So on the right-hand side, you can see there are still a lot of spikes, and the vertical axis is the total number of database connections that we have. So you can see as time moves forward, we are the number of database connections kind of taper off and stabilize. Now, one thing that's worth noting is this spike. This is the time that we actually had to use the global switch to kill proxy SQL because there was a misconfiguration in proxy SQL. Somehow I mistakenly put in the wrong IP, and that stopped a bunch of traffic. But luckily, we had a switch to kill to bypass proxy SQL completely, so we can debug. Now with this exercise, we're able to reduce the connections somewhere between 40% to 90%. So it was a huge win for us. Okay. Okay, so things were going fine in BDS 2021. We still have spikes when we deploy. That's understandable, but the spike is not as crazy as before. They are a lot more manageable. So things were going well until after BDS 2021, and then sometime in April, our production engineer was woke up to this. So this is a graph that shows our service delivery. So on the April morning, our site was offline for 4 minutes completely. As you can see the dips. So it was not fun. And then we began to look into the issues, and it turned out that one of the database that Google was hosting for us, they had a hardware failure. So when, as a managed service, when they notice a hardware failure, they kick off, they start a failover instance, but the process still took 4 minutes to complete, and that's why we were completely down. And then on top of that, because we're running in Kubernetes, and in Kubernetes, right, there are two types of checks that we can do on the pod to see if they're ready. One is called the health check, the other one is called readiness check. For the readiness check, in the past, we make the assumption that if one database is down, we're gonna take the whole thing down. And that assumption was set in probably 5-6 years ago, when Chrysalis was a lot smaller. So, what happened here? Database went down, the readiness pro checked to see that, oh, you have one database going down, so I'm not gonna send any more traffic to our pod. So nothing was going through the our pod until Google brings our instance back, and then we're back to close to 100% service delivery. And the sad part is, for that database, it was not in the critical path of our service. And I'll talk about what that means. So after that, we look at, and we began to think, how often is infrastructure unavailability? So we start digging into log, and then in proxy SQL, we found a bunch of statements or log entries about shunning server. What is shuns? What is shunning? So interestingly, proxy SQL does its own health check to the database. So every time it connects to a database, it runs a check, and if it fails, it will do a retry 3 times. And if it fails all 3 times, then it marks the database as shun, which means I cannot connect to it. So it would not make any new connection to the database until later. So if you look at the log, we see a bunch of them, and I didn't show the IP, but it was on different databases. So if you look at the left-hand side, this is the number of shun events that we have at 12 o'clock on a day. So infrastructure unavailability is a lot more often than we normally would expect. So earlier I mentioned that a database can be not critical to service or to serve Quizlet pages. So here's what I meant by that. On the right hand side, I have a page. We call it a set. So a set is a group of terms that you can put in, and then with definitions. So over here, I have some term and then some definitions. And I also have a star. The star means I'm interested to know more about this term for future studying. So I just mark it as a star. Now, what happens if the database that hosts information about the star term is not available? Well, we're going to take the whole site down. But if you're a user, it is probably acceptable that if that database is not available, maybe I just pretend that I have no star term in the set. So in that way, at least I can still study for my biology test tomorrow. And that's the thinking that we have. So now, instead of letting the database and the service die, we're going to try to return some kind of empty data back and pretend that you have no star term. For this example, you have no star terms in the set. So on our first attempt, the data engineer teams went into the ORM and then start to identify all the databases that are not in the critical path of serving. And this turns out to be a huge effort. One, the ORM was written many, many years ago. And then two, it was a solo journey. With a few of us went in, and then it was a huge effort to just put something back in to make it work. So unless you start building things and design things with reliability in mind, it is very, very, very difficult to retrofit that back in. So as a developer and a product designer, we're really good at knowing how something should work, but we're not really good at how something should fail. So in our second attempt, we tried to approach this differently. So we took a 3-step approach. First, increase the visibility of failure. And that was the slide that I showed earlier, is present visual to our friends in development, and let them know that there are a lot more infrastructure unavailability than we expected. So we try to raise the awareness of that by showing them the data. And then second, we try to lower the bar to get help. How do we do that? Internally, we develop a tool that if you enable a flag in your development stack, you can inject a fail or a bad IP to your database connect string. So that will simulate your page not able to connect to a database. And in that way, you can see what kind of exceptions are being thrown and how your page is affected by it. So now with this tool, they have a way to look at what a page looks like with failures. And then in the third step, we start to form more partnerships. Data engineering cannot do this, cannot raise availability and reliability alone. This has to be a joint effort and responsibilities. So as mentioned earlier, design with failure in mind. That is much more effective than trying to fix something that is already in production. So here's a timeline of what happened in our journey for the past 2 years. So after BTS 2020, we noticed a connection scaling problem. Then sometime in November and December, we work on a POC to look at distributed data store. And that turns out the lift was too big. It was too risky for us to use this type of technology. And then in April and May timeframes, we start to look into Proxy SQL. And finally, in July, we're able to roll Proxy SQL into productions to help with optimizing the traffics, the database connections between our web app and databases. And then in April, we have a service interruptions that help us to realize we have a lot more problems with our infrastructures in terms of availability. So we began to develop tools first by trying to do this alone, modifying the ORM and fail. And then we were going to solicit help from developer, and we give them tools so they can see what kind of failures that we'll get when a database is not available. So now we're in BDS 2022, and hopefully after October, when things are settled down, we can continue to have tighter collaborations. So here's what we learned in the past 2 years. Right, start with something small and iterate. When we first started with Proxy SQL, we didn't know where we would end up. We just thought that it would be a way that we can basically lengthen our database runway. Okay? So start something small, going from 0 to 1 is still much better than nothing. Revisit past decisions and assumptions. Right? So, decisions that we made years ago when Quizlet was much smaller may not make sense anymore. Right now we're serving close to 50 million active users a month. So taking down the database is going to have, or taking down the services because of infrastructure failure, is going to have a much bigger impact than what it used to be 5 or 6, 7 years ago. Also show, don't tell, give people tool to look at data, to see the problems. Right? Telling them doesn't really help. And then try to foster a collaborative cultures between system and developer. Right? Sys and dev working together is always going to be bigger than sys or dev working alone. So through different internal discussions, we kind of came up with 4 North Stars for our database reliability. We want it to be resilient to failures. We want to be using the suitable data store for whatever product that they're building. And that is not just from the performance or technological perspective. Cost is also a concern. I think someone asked me about Cloud SQL versus Spanner before. Spanner is a lot more powerful, but very, very expensive. We also want to minimize latencies. We're working on growing up our users internationally. So if we can have something that is closer to them and serve them faster, that would be great. And that takes us to having data stored in a high availability fashions. This can also help with disaster recovery. So this is something that we came up with after talking with the developer. And it has to be a joint effort. Otherwise, data engineers can't do this alone. And thank you for your time, and I can take questions if there are any.
Can you explain a little more why proxy SQL is better? Like what it does differently than MySQL?
Proxy SQL is a proxy. So MySQL is the database clusters. I should repeat the questions. The question was, how is proxy SQL better than MySQL? So there are 2 different technologies. MySQL is the database, and then proxy SQL, think of it as a traffic manager that helps manage the traffics between your applications and database. And multiplexing is just one thing that we are currently using. There are other really neat features. For example, they can look at your query itself, and then you can apply rules and say, I want to send this query to X database. So this is something that we're looking at, and it can help us when we begin to look at distributed data store again.
So can it do caching as well?
Can it do caching? It can do caching as well, but you have to be careful that caching means you have to give it a lot of RAM. Yeah. And the way that we're running proxy SQL, we're not running a single proxy SQL. We're running this in Kubernetes, so we have multiple pods. Now, when you go through caching, it's possible that it goes through pod A the first time, and the second time it goes through pod B. So in that way, it kind of defeats the purpose of caching.
And you run one proxy SQL per node?
Not per node, because I think our footprint, we have something like 200 or 100 something nodes in the GKE itself, but we're only running 16 pods of proxy SQL, and that's enough to handle all our traffic for now. Anything else? All right. Well, thank you very much for your time. My name is Mason, and have a great rest of your day.